So in this lesson, we're going to look at rates of change. And this is primarily review, but it's a very important topic, so it's worth spending an extra bit of time on it. The idea is we're going to have two quantities. And we're not going to be given graphs, we're going to be given functions that are written out. But thinking in terms of graph is very helpful. I'm going to label these axes x and y, but the two quantities that are being represented might be time versus distance or all sorts of different things here. And then we'll have some function, some expression here that gives y as a function of x. And there's two sorts of rates of change that we're going to be concerned with. I'm going to abbreviate rates of change ROC in this lesson. The book does the same. The first is average rate of change. An average rate of change is between two particular values, say x0 and x1. An average rate of change is the ratio of how much y changes versus how much x changes between these 2 points. In other words, average rate of change graphically is the slope. This slope here is the average rate of change between x0 and x1. And the way we compute it is we do y1 minus y0 over x1 minus x0, or, since y is a function of x here, f of x1 minus f of x0 over x1 minus x0. This is just a slope calculation. Here we have the change in y, here we have the change in x, so the average rate of change between these two values is given by this expression. And then if I want the rate of change at a particular value, so that would be the slope at this point. That, of course, is given by the derivative. So the rate of change at a particular value is the slope at the value, and that is just the derivative of that function at that value. So the rate of change at x0 is just the derivative of f evaluated at x0. So if I talk about the rate of change between two values, it's a slope calculation between those 2 points. If I talk about the rate of change at a value, it's the derivative at that point. Let me do an example from physics. So here's an example from physics. The Earth exerts a gravitational force of F equals 2.99 times 10 to the 16th over r squared newtons on an object of mass 75 kilograms. Excuse me. When is the distance r meters from the center of the Earth? So, first question, find the rate of change of the gravitational force as the object ascends from the Earth centimeters to 10 kilometers above the Earth's surface. So this is the rate of change between two values of r. So here we have f as a function of r. So if we were going to think graphically, we've got f and r. And we want to know the gravitational force, rate of change of the gravitational force as it goes from the Earth's surface. So there's my first value of r to 10 kilometers above the Earth's surface. But what does r represent? Well, r is distance from the center of the Earth. And we're not told that distance anywhere in this problem, so we're going to have to look it up. So if I look it up, I get, well, let me see, I got this from this textbook here. The radius of the Earth is 6.77 times 10 to the 6 meters. So as an object ascends from the Earth's surface to 10 kilometers above the Earth's surface, so that means r0 is at the Earth's surface, and r1 is 10 kilometers higher. So that would be 6.77 times 10 to the 6th plus, you see 1 kilometer is 1,000 meters, so this is 10,000 meters. So let me see if I remember my scientific notation here. Let's see, this would be, I think this would be 6.78. Yeah, 100,000 would change this, so this is 6.78 times 10 to the 6th meters. I hope that's correct. I'm not sure. I'm going to have to think this through. Wait, 6. Yeah, so that's... Yep, I was right. Okay. This is that. I had to remember my scientific notation. So this is 6.77 times 10 to the 6th. Then I'm adding 10,000 meters. There we go, that's right. So, I want to know the rate of change of the gravitational force. So I want the change in force between these two values. And then I want the change in the radius. And the change in the radius is clearly 10,000 meters. So I want F of R1 minus F of R0 over R1 minus R0. So F of R1 is, using my formula up here for the gravitational force, 2.99 times 10 to the 16th over 6.78 times 10 to the 6th squared. Then I want to subtract 2.99, this is F of R0, times 10 to the 16th over 6.77 times 10 to the 6th squared. And this is all over the change in radius, 10,000 meters. Notice the units here are going to be, this is in newtons up on the top, this is meters, so this is going to be newtons per meter. The average rate of change is newtons, which is the measure of force, per meter. And this is now a calculator mash. So if I get out my calculator and work this out, do I want to take the time to work this out? I'm not going to take the time to work this out. This is newtons per meter. So let's focus on the next part of the question. You have to work this out in your calculator using scientific notation carefully. But I don't want to take time for this in this video. Part 2. Find the rate of change on the force of the force on the object at the Earth's surface. So now this is at a value rather than between two values. This is going to involve the derivative. So
here's the force formula again. I need to take the derivative of this. Now this is just a big ugly constant. I could use the quotient rule here, but a better way is to write this as times r to the minus 2. So this is just a constant times r to the minus 2. So the derivative, f prime of r, this multiplicative constant just sits there. And then we have times minus 2r to the minus 3. And then I want the change at the Earth's surface. And if we go back, the change at the radius of the Earth at the Earth's surface was 6.77 times 10 to the 6th. So that's what I'd have to put in here. And then use my calculator to get the value. So it'd be 2.66 times 10 to the 16th times minus 2 times 6.77 times 10 to the 6th to the minus 3. And what is that? That is using my calculator on the computer here. I get 2.66 times 10 to the 16th times minus 2 times 6.77 times 10 to the 6th to the minus 3. And calculator tells me this is minus 0.000171. Got three significant figures here. And this is newtons per meter. This is very, very small. And that agrees with our experience. When we're near the surface of the Earth, the rate of change of the force on an object changes very, very little. And so this is saying for each meter you ascend roughly near the Earth's surface, you're going to see the force decrease. This is negative by this tiny, tiny, tiny little amount. I mean, this is about 2/10,000th of a newton. It's a very, very small amount of force that you're losing here. And that agrees with our experience. So we don't see a large change in the force on an object as long as its distance from the Earth is not changing very much. So that's my example. One application of these rates of change is to use them to estimate small changes. And the idea here is straightforward. If I have the rate of change, or the derivative, at x naught, okay, that's giving me the slope of a tangent line, like so. And as long as I don't stray far from this point where I'm taking the derivative, then the tangent line should be very close to the actual value of the function. And so I can estimate I can use the slope at f prime of x naught to estimate small changes in f from x sub 0. Remember that slope is change in y over change in x. And the derivative is s is telling me the slope at this point, and is a good approximation to the function as long as you stay near this point. The tangent line and the function will remain very close. So I could say this is approximately equal to f prime of x naught as long as I stay near x sub 0. If I move far away, if I go from here to say here, the tangent line slope is no longer following the curve at all. It's going way, way far off. But if I'm saying near here, I can use this derivative to estimate small changes in whatever y is as a function of x. In particular, if delta x is 1, if we're doing a unit change, then the change in y is approximately equal to the derivative. Now that has to, for this to work, the slope can't change very much in changing x by 1 unit. So if 1 was from here to here, then that would be a bad estimate. But if 1 is just a small change, it depends on the scale of our axis here. If 1 is just a small change, then this would be a very good estimate. The change in y, if we change x by 1, y is going to go by approximately the slope or the rate of change at x sub 0. Let me show you this in an example.
Let's say we have a function in the past that we know that is good for estimating the cost to produce a certain amount of bagels. We've got our bagel shop, and here's our cost function. The cost to produce x bagels is c, 300 plus 0.25x minus 0.5 times x over 1,000 to the third power. This is in dollars. So first let's compute the rate of change at 2,000 bagels. So that's going to be the derivative. Rate of change at a value is the derivative at that value. So I need to get c prime. So the derivative of this, derivative of 300 is 0. This is a constant times x, so I'll get
0.25. Then I have this thing to the third power. So the cube comes down. Let me make sure this is clear. Multiplication squared. And then I have to use the chain rule because inside here wasn't just an x. I have to multiply by the derivative of this. The derivative of the inside is 1 over 1,000. And so if I simplify this, I get 0.25 minus, this is 1.5 over 1,000. So that would be, let's just do 1.5 over 1,000. Since my ability to do mental arithmetic appears to be impaired today. Then I need this evaluated at x equals 2,000 bagels. So C prime at 2,000 is 0.25 minus 1.5 over 1,000 times 2,000 over 1,000 squared. So this is 2 squared is 4. 4 times 1.5 is 6. This is 6 over 1,000. 6 over 1,000 is 0.006. This is 0.0244. And my units here would be the units of my function divided by the units of the input. So this is dollars per bagel. So my cost, rate of change of cost at 2,000 is a little less than a quarter per bagel, quarter of a dollar per bagel. What does that mean? Well, let's estimate the increased cost to produce 2001 bagels instead of 2000. So we're going to use this derivative, and it's, since we're going from 2000 to 2001 bagels, my change in bagels is 1. And remember that slope here is going to be a change in cost over change in bagels, and that's approximately the derivative. This is C, and we got that as 0.244. Since we're changing bagels by 1, I love writing delta bagels. I find that hugely amusing. Since delta bagels is 1, we get the change in cost is approximately 0.244. So it's going to cost us about a quarter if we want to go from 2001 bagels instead of 2000. That's the derivative, because that's we're increasing by 1. Now this is assuming that the slope here is staying close to the curve, that at the scale, if we were to graph this function here, that the slope is not changing very rapidly at 2000. And the way we could measure that was with the second derivative, but that would be beyond what we want to do with this lesson. Last thing though, is what's the actual cost of producing 2000 and 2001 bagels, and was this estimate accurate? So the actual cost of producing 2000 and 2001 bagels would simply be 2000 and 2001 into this function and work it out. So I would have to compare and C of 2000.
And I've done that ahead of time. C of 2000, the cost to produce 2,000 bagels is $796. And the cost for 2001 bagels, this is just putting numbers into this function. The cost for 2001 bagels is $796.24. So was the estimate accurate? Well, you tell me. Well, you can't because you're watching a video. It went up 24 cents, and our estimate was to go about 0.244, so I think our estimate was pretty accurate.